starting from something we like in physics, Hilbert spaces, we can boost it up from a set to a category. We can do that in lots of places in physics. For example, in topological quantum field theory, we like to think about this category NCOB, where the objects are n-1 dimensional manifolds, usually compact oriented and smooth, and the morphisms are cobordisms between those, that is, manifolds with boundary, where you take some part of the boundary and you call that the source of the morphism, and some part the target. So this picture here is a morphism from two circles to one circle. So the reason why we like to do that in physics is we like to study simple imaginary universes where here, for example, space is just one-dimensional. So space could be two circles, and space-time is two-dimensional. So this could be a space-time, and it allows us to study fun things like what would happen if two universes collided into each other and turned into a single universe. You can write down quantum field theories of a simple sort that only depend on the topology of these manifolds. And they're called topological quantum field theories. And you can calculate with them, and you can learn some things about physics, even though it's very simplified physics, both because it's lower dimensional and because it's purely topological. But you can go up a notch and think about a bicategory. Hi, Riverside. You can tell what school I'm at. Where we look at n-2 dimensional manifolds, cobordisms between those, and then cobordisms between cobordisms. So here, for example, we have so this is a picture of some one manifolds, some two manifolds, and a three-dimensional manifold, which is this whole three-dimensional picture here. So abstractly, what I'm talking about here is a two-morphism in this bicategory 3-cob sub 2. The objects in this picture are both, in both cases, a circle, I guess. Sorry, gotta be careful. Let me think about what I'm saying. So, no, I'm sorry. So this is the empty set, and this is the circle. This here is a cobordism from the empty set to the circle, which looks like the top part of the picture. So this thing, drawn in a more smooth way, would be an example of a cobordism starting at the empty set, and it's a two-dimensional manifold going from the empty set to the circle. The bottom part of the picture is another cobordism from the empty set to the circle, namely just a disk. And then the three-dimensional thing itself is a cobordism going from this to this. So this would be the kind of thing you might draw if you were studying physics of a simple universe that had three-dimensional space-time. So space is two-dimensional in this picture, and space, for example, started out having a wormhole in it. Physicists have nice names for everything. This handle would be called a wormhole. It would be a way of getting from some portion of space over to another portion of space by going through a magical tunnel. And then at the end of the day, the wormhole has disappeared. It's not there anymore. So people who study things like quantum gravity are interested in things like the creation and annihilation of wormholes, and this is the kind of picture you would use to describe them. But the difference is that now I'm actually including in my description of the situation also some one-dimensional aspects. I'm allowing these to themselves be cobordisms from a manifold to another manifold, or one-dimensional. And that's useful because it allows us to put together pieces of space. So I could take this cobordism and I could compose it with something else, which would then correspond to sticking together chunks of space.
Mr. Abbas,
Yes.
the two cylinder here
Yes.
is the cylinder here.
It's the cylinder and also the solid, also the stuff inside here. So it's
Yes, of course.
Yeah.
Yes, because it's a part of the two cell.
Yeah, so it's a solid cylinder with a handle, with a solid handle attached. Mhm.